Hello everyone, and welcome to OneClass. My name is Jeff Krause. I have a PhD in physical chemistry, and today I'm going to run through a few undergraduate level physics questions. So here's our first one. So it doesn't show the figure, but I'll just draw it. So it says in the figure, we have a resistor attached to a circuit with a bar that is able to slide over it without any resistance. The resistor here is 11.3 ohms. This distance here is our L, and L equals 0.43 meters. And it is inside a uniform magnetic field of strength 0.74 Tesla. Okay, and it's all coming out of the page, so B is 0.740 Tesla, and this moves with the velocity V. And it asks, the question is, what speed would you need to generate a current of 0.135 amps. Sorry. So what speed would we need to slide the bar to generate a current of 0.135 amps? So this is a flux and Faraday's law question, where the flux we're dealing with is that within the circuit. Which doesn't actually matter too much, or the changing, and we're dealing with a volume change, right? So our flux is our B field dot our area, where our area would again be that within the circuit here, or what we're going to actually use is our area is just going to be L, which is our distance here, times our x, so our x coordinate. And so, and then to give it, because it's a vector, I'm just going to say it's out of the page, and I'm going to define some axes here. So this would be x, y would be up, and then z would be out of the page. So this would actually just be k hat, and our B field is, of course, B k hat, as it's all coming out of the page. And so our flux is just B dot A, k hat dot k hat is just 1. So we can actually just write this as BLX. And then from Faraday's law, we have that our electromotive force is minus the derivative of the flux with time. So if we take the derivative of these quantities, our magnetic field and our length there aren't going to depend with time, so we can take those out front and write it as dx by dt. But of course, dx by dt is our velocity. And so it's just BLV. Now, I got some extra stuff. Now, if that's our electromotive force, and the negative sign just means that it's opposing the direction, it's opposing the direction of increasing flux. So as we move to the right or in the positive x direction, the flux is increasing upwards. Now I'm trying to remember how the current is going to go. I'm just not going to bother with that. Okay, so we've got our potential, so our electromotive force, but then it wants to know such that the current through the resistor is 0.135 amps. So we have our resistor there, and we know from Ohm's law that V equals IR. So in this case, our voltage is our electromotive force, and we can kind of chop the sign off here because the sign would just change our direction of current flow. Okay, so we don't really need to worry about what direction the current's flowing in this particular case. We just need to know the voltage that's being dropped. So we'll use the unsigned. So BLV is IR. And so now we have all the quantities that we need. And I'm going to go ahead and erase some of these so I can solve for our speed. So now our speed is IR over BL, which is going to be 0.135 amps times our resistance, which is 11.3 ohms, divided by our B field, 0.740 Tesla, and our length, 0.43 meters. And if we run this through on our calculator, we get 4.794. And just as an exercise, so this is in angstrom amps, ohms per Tesla meters. So an ohm is a kilogram meter squared per second squared amp squared, and a Tesla is a kilogram per second squared amps. So these units, so an amp ohm per Tesla meter is an amp kilogram meter squared per second squared amp squared, all over kilograms meters, kilograms per second squared amps meters. Okay, so then this meter is going to cancel with that guy. This amp is actually going to end up here, and it's going to cancel with these two. And these kilograms are going to cancel. And this is the reason never to try things. So, what am I missing? Second. Oh, sorry. So the ohm is actually seconds cubed. There we go. So that should be seconds cubed. So then that'll leave it per second. And so this is just meters per second. Which is the appropriate units you should get out. So that's good. That means we didn't make any mistakes. So there's our speed. Okay, so if we check the solution, it just has the final answer, so that's okay, it is correct, but it doesn't really show you how to derive it. So I'd say it's correct. Okay. So our second one here, I'm definitely going to have to draw. Okay, so we've got a power line with a line running, and that's 7 meters. And then below it, a farmer has a 2 meter high and some length. So it's got a coil of wire. That's a rectangular coil that's 2 meters by some length. And there's 10 turns of coil there. So the 10 turns are going into and out of the page. Okay. And through this line, there's a current running. And it's actually a sinusoidally varying current. So our current is actually I naught sine omega t, where omega is 2 pi f, and in this case f is 60, so 2 pi times 60 per seconds. So that is that's our frequency for our current. And so we're going to get a B field that's emanating from this line, which is going to pass through our loop. Which is going to pass through our loop at different intervals, and so we're going to get a changing flux and therefore an EMF generated in the coil. The question asks, we need 170 volts in the coil, so for what L, so what length of our coil would we need to generate a voltage of 170 volts. And also it needs to be 60 hertz varying, but we'll find that will just come out from the current itself being 60 hertz varying. Okay, so how are we going to approach this? Well, to find a voltage that's induced, we're going to need to use Faraday's law, so minus d phi by dt. We have actually not one coil, but 10 coils. And so we're actually going to use kind of the coil version of this, which is n d phi by dt. So the n here, I'm just going to put an arrow instead of an equal, just because I'm doing it for coils. So both of these should be equivalent, but here this phi is referring to a single coil, while this phi would be referring to all the coils. But I'm just going to use this guy. So what is our flux? So let's find that first. So now to find the flux, I'm also going to kind of redraw the relevant parts. So here is my coil, which is 2 meters high. And actually that doesn't matter for me too much. I'm going to leave that out. But here's my line, which is 7 meters high. And I'm going to get a B field at the very tip, which is at 5 meters. And I'm going to also get a B field that's at the very base, which is going to be 7 meters. Okay? Now, the length is L. And my B field from a conducting line can be found as mu naught I over 2 pi r. So it is an R-dependent B field. But my flux is typically defined as B dot A. But in this case, I'm going to define it as d phi is B dot dA. So some incremental flux is B dot dA, where now my dA is going to be for a small area of length L and width dr. And then I'm going to integrate it from 5 meters to 7 meters away from the power line. So my d phi, or my dA, sorry, is L dr. And if I want to make it a vector, then I can, and it's just going to be k hat, right? Because my area lies in my xy plane. So if I go x, y, and so from the right-hand rule, the area, the unit vector for the area comes out of the page. But also my B field follows the right-hand rule. So if I run my thumb along this direction, then my fingers coil in the direction of the field. So that means that the field is doing this, or approximately at the area they will be going into the page. So my B field is either minus K or plus K, depending on how the voltage is varying. And remember that our current, or as the current is varying, sorry. Remember our current is sinusoidally varying. That means that it takes values of plus I naught and minus I naught, so it's going back and forth. So at any time the B field is going to be into or out of the page. Meaning that, but the point is that our d phi is just going to be our B field times our dA, because they're always going to be aligned. But I am going to use an absolute value here. Maybe I won't actually, I'll let the sign kind of take care of itself. Yeah, I'll let the sign take care of itself because it'll always be in the k hat direction, but the sign of omega t will give us our plus or minus sign. So that should be fine. Okay, so it's B dA, and so that's B L dr. And so now we want our total flux. So we need to integrate it from 5 to 7. So our flux is the integral of BL dr from 5 meters to 7 meters, which is just the B and L, and now filling in for our B field from above. So this is then the integral from 5 to 7 of mu naught I over 2 pi r L dr, which now we can bring out many of the constants. So mu naught I doesn't depend on the radius, and neither does the length. And so this is just integral from 5 meters to 7 meters of 1 over r dr, which is just a ln. So it's mu naught I L over 2 pi ln r from 5 meters to 7 meters. And so then this is just mu naught I L over 2 pi ln 7 minus ln 5, which comes out to be mu naught I L over 2 pi ln of 7/5. Just using the ln rules, which is if you subtract them, you can then subtracting 2 lns is the same as dividing by what's inside. And so then there's our flux now. Okay. So in this case, it's the current that's time varying, and it's going to result in our EMF. So now we can solve for our EMF. So our EMF is just minus n for the number of coils, d phi by dt, which is minus n, d by dt of all this. Okay. And then minus n. So our mu naught isn't time dependent. Our L is not time dependent. This is not, and this is not. So it's just di by dt. So our I is I naught, our I is I naught sine omega t. So di by dt is just, so I naught is not going to, that's not going to be time varying. So it's just the sine omega t, and so that's going to give us an omega out front and a cos omega t. Okay, so then now our EMF is just minus n mu naught L over 2 pi ln 7/5 I naught omega cos omega t. And so it's asking for our peak value, and so cos omega t is giving us our time varying. So that makes it 60 hertz, but it goes between -1 and 1, and so honestly the only way we're going to get a max or a peak value is when this is equal to 1 or -1. And so our peak voltage is just going to be the rest of this, right? So N, so this is our max. And we want this to be equal to 170 volts. We have all of our values now, and so we can start to plug them in. So it's 10 turns of coil. I'm going to get rid of this equal. So there's 10 turns of coil, so N is equal to 10. Mu naught is a constant, so it's just 4 pi times 10 to the -7. I better not drop units. 4 pi times 10 to the -7 newtons per angstrom squared. L is our length, which we are solving for, so I'll just leave it. Over 2 pi. ln of 7/5. And then our current is given as 55 kiloamperes, so times 10 to the 3 amperes. And our omega is 2 pi times 60, 2 pi 60 per seconds. And now we can rearrange this for L. And so this all equals our 170 volts. So we can rearrange this for L and say that L is 170 volts over, I guess, times 2 pi. And then all over the rest of this. So 10, 4 pi times 10 to the minus 7 newtons per angstrom squared, ln of 7/5, 55 times 10 to the 3 angstrom, not angstroms, amps, 2 pi times 60 per seconds. There we go. Okay, so we do have a little bit of cancellations here. So this 2 pi, we can dump that with, and that's pretty much it. Also, a volt is a newton per amp second is a volt. Newton per amp second, a newton meter per amp second is a volt. So I'm just going to actually erase the volt, write it in as a newton meter per amp second. And so our newtons will cancel. This amp is going to build up with this and cancel with that. So those will cancel. And then the per second over here will cancel, leaving us with meters, which is good because that's the answer we're looking for. And then if we run this all through on our calculator, we would get 170 over 13.953 meters, which is 12.18 meters. And so there we go. So the length of our coil to generate that 170 volts would have to be 12.18 meters. Okay. All right. So then, if we check our solution here, there is none. So it's obviously incorrect. So I guess I'll just say the solution is incorrect. Okay. So for the third one here, I'm going to do a couple circuits. So we've got A, and I'm just going to draw it and then fill in the extra information. So we've got R1, R2, and R3. And it says that if A is connected to B, through a 150 volt EMF, and we're given that R1 is equal to 150 ohms and R2 is 50 ohms. What is R3? I1 and I2. such that our total current is 1.00 amps. Okay, so the first thing we're going to need to do is, or the first thing we can do, I suppose. No, the first thing we'll have to do is compute our equivalent resistance in here. So our equivalent resistance is given as 1 over R is 1 over R1 plus 1 over R2, which is 1 over 150 ohms plus 1 over 50 ohms. And so our equivalent is 37.5 ohms. And so then we can compute our voltage drop across this equivalent resistance, as now if we were to redraw the circuit, we really just have A to B, and we have this R equivalent here, and R3, and we know we have 150 volts here, 0 volts here, and so then our voltage drop across our equivalent resistance, we have to drop our full 150 volts, so that means that our V1, and we know that we have 1 amp going through the full circuit, and 1 amp, and our total current, our current along a serial line has to be all the same, so that means our current here is 1 amp, and our current here is also 1 amp. So our V equivalent, so our voltage drop across the equivalent resistance, is given by Ohm's law as IR equivalent, which is just 1 amp, not an angstrom, times 37.5 ohms, which is 37.5 volts. And then we know, because we have to drop the full 150 volts, that our voltage drop across 3 has to be 150 minus 37.5 volts, which is 112.5 volts. So we have to drop the full 150 across the circuit. We know that we've dropped 37.5 across the equivalent, and so therefore we know that the drop across the resistor 3 will have to be this. And so now we can say through Ohm's law that our R3, I really want to make that a B, that our R3 is our V3 over our I, which is 112.5 volts over 1 amp, which is 112.5 ohms. Okay, so there's our R3. Now, to compute I1 and I2, we use the fact that we don't use that current is the same, but instead that voltage is the same in a split. And we know that the voltage drop in the equivalent resistance is 37.5. So that means for our split, the voltage drop across both resistances, R1 and R2, is 37.5 volts. Okay, so we know that the voltage drop here is 37.5 volts, and that the voltage drop here is 37.5 volts. So then we can easily compute the current, right? So V1 is 37.5 volts, is equal to I1 R1. So then I1 is 37.5 over our R1, which is given as 150 ohms, which comes out to be 0.25 amps. And we know that V2 is 37.5 volts, which is I2 R2. So then I2 comes out to be 37.5 volts over 50 ohms, which comes out to be 0.75 amps. The nice thing here is that our total current from our split, so I1 plus I2, should equal our total current, which is 1 amps. And if you look, if we sum it up, they do. So that means we didn't make a mistake. And there's everything that the question asked us to compute. Okay, so R3 is 112.5 ohms. And then I1 and I2 are their respective values. Okay, so if we check to the solution, equivalent resistance, 112.5 ohms, so there's our R3. Current through R1 is 0.25, R2 is 0.75, so that looks good. And I'll submit that. Okay. So here we've got a man holding and I'm just going to draw this kind of sticky, but it's the best way I can do. So this is an arm holding a ball. Okay. And the ball weighs 178 newtons. And that should be straight down. Any deviation from straight down is just my lack of drawing ability. The center of gravity of the arm is about here, and the arm weighs 22 newtons. The muscle in the arm pulls up about here and is labeled M. And then the arm bone would also apply a normal force. The distance is in here, so the distance from the pivot of the arm to M is given as 0.0510 meters. The distance from the muscle to the center of gravity of the arm is given as 0.0890 meters. And the distance from the pivot to the center of gravity of the ball is 0.330 meters. And so we're looking for two things. The value of M and the value of N that I've shown in this figure. So to solve for the value of M, we're going to use that, well, the arm is stationary, so everything is stationary. So to solve for the value of M, we're going to use that nothing's rotating around this rotation point. And so everything's going to be related from there. And so what I mean by that is that the sum of our torque, which is equal to I alpha, is 0. So the sum of our torques is equal to 0. And now we can go through and figure out all our torques. So for our N here, so R equals 0, or our torque is equal to F cross R, right? And in this case, our R is 0, and we can write this also as FR sine theta, where theta is the angle between F and R. But R is 0, so then I'm just going to label this a bit better. So for our N force, this equals 0. So for the normal from the elbow joint is 0. For our M force, our torque is F cross R, which in this case is M R sine theta, or I'm using M for the force. Now we need to use the right-hand rule to determine directionality here, just so that we know which one should be negative and which one should be positive. So remember, the right-hand rule is you put your fingers, or at least the right-hand rule that I use, you put your fingers in the direction of the first one, so in this case the force, and then you put your palm in the direction of, so I'm just going to redraw the M force, and you stack them tail to tail, so there's the R, and so you put your right hand fingers in the direction of the force, and then your palm should be in the direction of the R, and then your thumb points in the direction of the torque. So in this case, our torque is into the page, and I'm going to go ahead and define that as a negative torque. So I'm just going to augment this and say that this is minus mr sine theta. Our theta here is 90 degrees, sine of 90 degrees is 1, and so I'm actually just going to get rid of that too. So then it's just minus mr. Okay, so for our center of gravity here, so I'm just going to call this our mg force. So torque is F cross R, which is equal to 22 newtons is the force, and the R is, actually I'm going to plug this in here too. So the R that we were given for our M is 0.0510 meters. And so this distance here is, I'm actually just going to draw it down here just for space, 0.0510 meters plus 0.0890 meters, which is 22 newtons, times 0.1400 meters. Okay, and again, if we apply the right-hand rule here, the force is going downward, the radius is outward. So then our force is coming out of the page, and I'm defining that positively. So this guy's a positive torque, whereas for M, it's a negative torque. And then for the ball, we have very similar. Our torque is F cross R. In this case, our F is the 178 newtons, and our R is the 0.33. If we look at the direction, it's the same as for our mg force, so it's going to be positive. And so this is just going to be 178 newtons times the 0.330 meters. Okay, so now we have our torques. So now our sum of our torques is 0. And so our sum of our torques, if we write out all our torques here, so we have 0 plus, and we don't really need to include the 0, but I'm just doing it for completion. 0 minus m 0.0510 meters plus 22 newtons times 0.14 and plus 178 newtons times 0.330 meters. All that equals 0. So now we're in a perfect place to rearrange this for m. And so our m times 0.0510 meters is equal to 12.2 newtons, or our m Newton meters, I should say. And so our m, oh, okay, never mind. I'm just gonna erase that because apparently I did not calculate the intermediate, so our m is 12.2 newtons, which is just 1.2122 times 10 to the 3 newtons. So significantly larger than the other forces. Now to compute our n. To compute our n, we will use not our rotational relationship, but our linear relationship here. So if m is that, so our sum of our forces is equal to ma, which is equal to 0 again because nothing is moving. So our forces, if we look, and we can easily determine direction, I've got the n acting downward, as well as all the weight forces, and the m acting upwards. So sum of our forces then is just minus n plus m minus 22 newtons for the arm mass and minus 178 newtons for the ball mass. And we actually could have put in the value there, but I'm just going to rearrange and move n to the other side. So n is equal to 1.2122 times 10 to the 3 newtons minus 22 newtons minus 178 newtons. And so then n is 1.012 times 10 to the 3 newtons. And then so there is our normal force from the bone, from the elbow joint. If we check our solution here, we have, given that n is upward, so there's the 1.21 times 10 to the 3, and there's the 1.01. So I would say it's correct, although likely a little harder to follow. Okay, so I'm just going to draw this one. So we've got a roof. From it is hanging an inverted A. Like this. And we've got it hanging from 2 strings. Like this. And the length is equally split, where that is L and that is L, and this is also L and L, even though it might not look like it. And so it wants to know what force the crossbar applies on the sides. And not just what force the crossbar applies, it's not just that. So we have masses for our sides here. So each of the legs has a length of 2L and a weight of 120 newtons. And the center we can put there. So the weight here is 120 newtons. And it just wants to know the force applied by the crossbar. So first of all, we can find the values of our tensions here by using F equals ma. So if we've got 120 newtons there, and we've got 120 newtons there, and so from F equals ma, or the sum of our forces equals ma, we know this equals 0 as it's not moving. Our only forces here are our tension forces, and we would assume, as it's equally distributed, that both tensions are actually the same. So I'm just going to leave it as T plus T, like that. And then plus our weights, which is 120 equals 0. And so we can easily see that our tension here is 120 newtons. So each of the tensions are 120 newtons. So now if we consider this rotational point, that way we don't have to worry about the force of each leg on the other one. So that makes it a bit easier. And so the forces here are our gravitational force, our force due to our crossbar, which I'm going to label as Fc, and our tension. And I'm going to just solve it the way I've got it all drawn out here. And it does give us that this angle is 60 degrees. All right. So now for each of our tensions, or to solve this now, we need to use that some of our torques is I alpha, which is 0 because it's not moving. And now we need to figure out each of our individual torques. So let's start off with our crossbar, and I'm just going to re-sketch it here. So we've got an R of L, and then we're applying our crossbar force. To calculate our torque, which is F cross R, we need our angle, because we can rewrite this as F R sine theta. And to get our angle, we need to put these two tail to tail. So our FC is actually here, and so we need this theta. So we're given that we've bisected this angle here, so this angle in here would actually be 30 degrees. This is 90. So our theta in this case is FR sine 90 plus 30, which is equal to FR cos theta, or FR cosine of 30 degrees. Which, if you're good with trig, you'll recognize that as root 3 over 2. Also, we need a sine on this guy, and so we're going to again use the right hand. We're going to use the right hand rule, and so the way that I do it is put our fingers in the direction of the force on your right hand. And then your palm is in the direction, Those are roughly fingers. Our palm is in the direction of the L, and then your thumb is in the direction of the force. So in this case, it will be out of the board or out of the page, which I'm going to define as my positive. That is not a very nice hand, but it's okay. Okay, so then there's our FC torque, and now our mg torque, or our mass. So our torque, I'm just going to redraw it again actually. So that the mg torque is going to be applied at L. So our R is L, and our mg is 120 newtons. And again, we're going to put it tail to tail. And it's this angle in here that we need. Again, it bisects the angle, so that would be 30. In here would be 60. And so this angle is 60 minus 90. So our torque is F cross R, which is Fr sine theta, which is Fr sine of 60 plus 90, which is Fr cosine of 60, which is a half. So cosine of 60 is a half. We do need a sign on this, so our force is downward from the right-hand rule. Then we would point the fingers downward with our palm facing the R, and our thumb would point in the direction of the force, which is in this case into the board or into the page, giving us a negative torque. And actually in this case, we do have quite a few of the values, and for this one as well, we had quite a few of the values, so this should have been FCR in this case is L root 3 over 2. And in this case, we have minus 120 newtons times L over 2, which is just minus 60 newtons times L. Okay, and then for our tension force, this guy is being applied at 2L, and it's going upwards, so there's our tension. That's L. Again, we want to put this tail to tail and find that angle, which is just going to be 30 degrees as it bisects the 60 degrees of the A. And so our torque is F cross R, which is just our tension times 2L times sine theta. And again, and now if we apply our right-hand rule, we see that this guy is coming out of the page. So this is a positive torque. And we have all of our values. So that's T times 2L times sine of 30. Sine of 30 is a half, and our tension value is found as 120. So 120 newtons times 2L times a half, which is 120 newtons times L. Okay, so then there's all of our tension values, or all of our torque values. So we have that our sum of our torque is 0, and so this is going to be just collecting them all together. Root 3 FCL over 2 minus 60 newtons times L plus 120 newtons times L Now rearranging and collecting terms, we can see that FC, and we can cancel all our L's here. FC is minus 60 newtons times 2 over root 3, which comes out to be minus 69.3 newtons. So the negative sign just means that I initially chose the FC in the wrong direction, so it doesn't pull the A in, it actually pushes the A out. But the magnitude of the force is 69.3 newtons. Okay, and so then sets the torques all equal to each other. Cancel, and we get that the force of the crossbar is 69.3 newtons. So that looks good. Okay, so here we have a thermodynamics question. And I'll just kind of summarize it here. So we've got 0.6 kilograms of aluminum with a temperature of 80 degrees Celsius. Also, our heat capacity for aluminum is going to be 0.900 joules per gram degrees Celsius. We've got 0.3 kilograms of copper at a temperature of 70 degrees Celsius. And our heat capacity for copper is 0.385 joules per gram degrees Celsius. And both of these are being placed in 1.2 liters of water at a temperature of 20 degrees Celsius. The heat capacity for water is 4.186 joules per gram degrees Celsius. And we're going to assume that the density for water is 1 gram per mil, meaning that our mass of H2O is 1.2 liters times 1 times 10 to the minus 3 mils per liter. So not minus 3, but plus 3, sorry. 1 times 10 to the 3 mils per liter times the 1.0 grams per mil, giving us 1.2 times 10 to the 3 grams of water. So now all three of these objects are placed together, and the question wants us to calculate what the final temperature is. So the key thing here is that delta H for our system is 0 when there's no, if it's isolated, which we're assuming in this case. And so each of the components must sum. So for the copper, it's going to be just MC delta T. Or actually for each thing, it's just going to be MC delta T. So I'm actually just going to take that off because it seems kind of pointless. So each of our delta H's is just going to be MC delta T. So we just need to sum to get our delta H for our system. We're just going to sum over each of the component delta H's. Okay, so then we have our water, which is M water, heat capacity for water, delta T water, plus our copper plus our aluminum. And now we can plug in some values. So for water, we had 1.2 times 10 to the 3 grams. Our heat capacity was 4.186 joules per gram degrees Celsius. And our delta T is our final temperature minus our initial temperature, which in this case, it's fine to use degrees Celsius, as everything is in deltas anyway. So that's our water. Now our copper, 0.6, 0.9, T minus 80 degrees Celsius. And our aluminum, okay, and the T here is always our final temperature. And so then all of this equals 0. Now, we can collect some stuff and rearrange. So I'm going to collect all the terms in T and do out all the relevant math. So what we end up with is T times 5.6787 joules per degree Celsius is equal to 151.749 times 10 to the 3 joules. Okay, so just collecting and rearranging to get to this point, and so then we can solve for our final temperature as 26.72 degrees Celsius. And so then there's our final temperature, and we should always check to make sure, especially in a question like this, and I think that makes sense, we have significantly more water, so the temperature should be pretty close to the water. If we check the solution here, basically the same. And so then it comes out to be 26.72 degrees Celsius, so that looks good. Okay, this one's a quick one. So we're asked the angle between the vector minus 25 m I hat plus 45 m j hat and the positive x-axis. So we can do this in a couple ways. So we can just sketch it. So there's the x-axis, the y-axis, and so this is extending it this way, so that's 25, and then 45 up, and so then the angle it's looking for is that one, as it's the angle between this vector and the positive x-axis. And so we can readily calculate this angle in here, as that will be tan of theta is equal to the opposite over the adjacent, so 45 over 25. So then theta is equal to 60. And so then our angle to the x-axis is 180 minus this, which comes out to be 119.05. Like I said, we can compute this in a couple ways. So we could do it this way, or we could use our dot product notation. So the x, the x hat unit vector is just 1 I hat. So then we could say that A dot x hat is equal to the absolute value of A times the absolute value of x hat times cosine of the angles between them. A dot x hat is just minus 25 meters. That's just following from dot product. So we just take the x component. So then rearranging, putting this, and then our absolute value of A is the square root of 25 meters squared plus 45 meters squared, which comes out to be 51.478. And so then we can rearrange this expression to say that cosine of theta is minus 25 over 51.478 meters. The meters will cancel. I should say that the length of x is 1. And I might as well put the meters in there. And so then that would be meters squared. And that will cancel. Okay. And then if we solve this for our theta, we would get 119.05. So either way, it will give the same answer. Okay. And so they use the dot product, although here we have, well, I guess that's just a multiplier. Yeah, okay. So that's the dot product, and then we get 119. So that looks good. Okay. So then for this question here, I'm going to draw it and go through some of the questions here. So we've got a battery connected by some thick wire moving to a thinner wire and then back to a thicker wire. It also gives that the lengths of each of the thick wires is 25 centimeters and the length of the thinner wire is 5.1 centimeters. Okay, and so the questions, or it asks which statements are correct. And the questions are, so I'll sketch on here, this is A point, B, C, D, E, F, and G. Is ID equal to IA? So is the current the same at point D as A? And in a steady state circuit, that is correct. So the current is the same everywhere, unless there's a split. But in a one-way circuit, the current will be the same everywhere. And even if there's a split, the current just splits. The current going into the split is equal to the sum of the currents. So it also asks, is EB is the direction of the electric field at B coming out of the page, and that is also correct. Out of page. And so the electric field is going to extend outward. and it asks, is the magnitude of the electric field at D equal to the magnitude of the electric field at F? That is our incorrect statement, because although the current is the same, the amount of charge in the smaller wire is not equivalent, and so our electric field will not be equivalent. And then the last question is the magnitude of the electric field at F equal to the magnitude of the electric field at C? And that will be correct, as the thicknesses of the wire are the same, the amount of charge should be the same, and so the electric field should be the same. Then it asks us to write a Kirchhoff loop law for this, starting here and going around this way, with the assumption that this is 1.8 volts and 0 volts. And using our electric field notation, so it wants us to use EF for the electric field at F and ED for the electric field at D. So to compute voltage drops, which is all Kirchhoff's laws, we're going to have a negative voltage drop, or a positive voltage drop going from positive to negative here, a negative voltage drop going from positive to negative, as we're going from 1.8 to 0 volts. Which is negative 1.8 volts. And then we're going to have negative voltage drops the whole way around, or positive voltage drops the whole way around, to get it to equal out. So then we've got, so just to expand on this a bit, I'm just gonna redraw here. So we've got a plus minus, a thick wire, and the thick wire's length is 25 centimeters. And then a thin wire, which is length 5.1 centimeters, and then a thick wire, which is again 25 centimeters. Okay, we know the electric fields, but we don't necessarily know the voltage drops, but we have three pieces here. So 1.8 volts, I'm going to call this A, B, C, plus delta V, A, B, C. I'm going to call this D, and I'm going to call this E, F, G, plus delta V, D, plus delta V, E, F, G is equal to 0. So that's basically our Kirchhoff loop there, where we're saying that in going from, if we go all the way around the circuit in this way, then we should have a complete voltage drop. So minus 1.8 volts plus each of the delta V's. Now, in terms of the electric fields, using the fact that we identified that our electric field in here, so B equals EF, for instance, and we know that they're all equal to EF, so that's EF, and here is ED. We've identified that all of these have the same electric field. Then we can use the fact that dV or delta V is equal to E delta X minus. And so then we just need to identify the appropriate delta X. Well, our delta X is the length of the wire. So our delta V ABC is just equal to minus EF times our 25 centimeters. Our delta VD is just minus ED times our length, which is 5.1 centimeters. And our delta V EFG is just minus EF times another 25 centimeters. Okay, and so our Kirchhoff loop is then just minus 1.8 volts minus EF times 25 centimeters minus ED times 5.1 centimeters and minus EF times 25 centimeters all equals 0. Okay, so now if we check through our solution and compare a bit. So as we said, the electron current at D is the same at A, and in fact should be the same everywhere. The magnitude of the electric field at F and C are the same, and the direction of the electric field at B should be out of the page. And those are the only three that are correct. And then our Kirchhoff loop is then negative 1.8 minus 25 centimeters times EF, which I could have put into meters, but we're not solving anything, so it's fine. Minus ED times 5.1 minus EF times 25. So that looks good. All right. And I think, okay, I can run through this one. So we've got 15 disks, which are all stacked together. And to solve for the moment of inertia, we need a couple things. So if I've got 15 disks, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And the center is there. And so they're all rotating about their central point. And so we want our full moment of inertia. And so it says that our mass is 135.0 grams, which is equal to 15 times our little masses. So each of the little masses. And our length is 1.4500 meters. And if we look at the little, if we expand one of the little circles, so we have an R, then each one will have a width of 2R, and so this is 30R. Okay, so that will just help us for later. Also, the distance between each of the centers is going to be increasing in increments of 2r, all the way up to the last point, which is going to be 2, 4, 6, 8, 10, 12, 14r away from the middle. And again, that will be helpful in a second. So the moment of inertia about a disk, about its center, is mr squared over 2. If we want to displace to a new axis, like this, where I have some distance L, then our mode of inertia is just the center of mass inertia plus ml squared. And so we can see that each one of the disks we can treat this way. And in fact, because it's the same on both sides, we can double up much. So we can see that our moment of inertia is going to be the sum of all our little inertias, which in this case is going to be the inertia for the center guy, plus 2 times that for 2 times that for the one that's next to it, as there's 2 of them. So that would be mr squared over 2 plus ml squared. So L in this case is the distance, so that's just this 2r. Okay, and then now there's 2 of the next nearest neighbors. So plus 2 mr squared over 2 plus m times 4r squared. And there's 2 of the next nearest neighbors. And 2 of the next nearest neighbors. Mr squared over 2 plus 8, m times 8, m times 8r squared. And again, the next nearest neighbors, and the next, and finally the last. Okay, so now there's quite a few there, and I'm just going to collect some terms here. And so this comes out to be mr squared over 2 plus 7 mr squared plus 1120 mr squared. When we do all this out, or 2255 mr squared over 2. Now we can make a couple simplifications here, right? So we said that L was 30r. So then L squared is 900r squared. And so then we can plug this in. But before we do that, we might as well use the full mass. And so our full mass is 15 times the little masses. And so our little masses are m over 15. And here as well, our r squared is L squared over 900. So if we do this, our mode of inertia is now 2255 ml squared over 27,000. Which, putting in the values for our mass and our length, times 135 grams and 1.45 meters squared. We get 23.706 grams meters squared times 1 times 10 to the minus 3 kilograms per gram. Comes out to 23.706 kilograms meters squared. Okay, so then the second part of this question just asks, oops, I forgot. The second part of this question just asks, what's the percent error if instead we had represented this as a rod? So if we had said that the moment of inertia was ml squared over 12, then we would have gotten a moment of inertia of 135. .45 meters squared over 12, which comes out to be 23.653 grams meters squared times 1 times 10 to the minus 3 kilograms per gram, which is 23.653. So it looks like an okay approximation just by I, but it wants us to compute a percent error. So our percent error here would be the known value minus the approximation over the known value. And all of it times 100%. And so this comes out to be 0.223%. So not too bad. Significantly less work and not too bad an approximation. Okay, so if we check through the solution here, we get 0.02371, so that looks pretty good. And if we approximated this in this way, we would get 2365, which looks pretty good, or 0.02365. And the percent error would be about 0.22 or 0.25. That would be just rounding differences, I assume. And so this looks good. And I'm actually going to stop it there and say thank you for watching. If you enjoyed this, please subscribe to the OneClass channel. If you want to leave questions, please follow the links below the stream or the videos. This has been Jeff Krause for OneClass, and